Room temperature ionic liquids, structure, properties, and applications. Room temperature ionic liquids, RTILs, represent a versatile class of molten salts composed entirely of ions, typically featuring bulky organic cations paired with inorganic or organic anions, with melting points below 100 degrees Celsius. Their unique physiochemical properties, such as negligible vapor pressure, wide liquid phase temperature range, and tunable solvation characteristics, have positioned them as promising alternatives to conventional solvents in diverse applications, including catalysis, separations, electrochemistry, and materials science. This video report provides a concise overview of RTILs, emphasizing their structural features, physiochemical properties, synthesis, and application potential, alongside current challenges related to stability, purity, and toxicity. Ionic liquids are broadly defined as salts that exist in the liquid state, typically at or near ambient temperature. Unlike traditional molten salts, which require high temperatures, for example, sodium chloride melts at 803 degrees Celsius, RTILs remain liquid below 100 degrees Celsius because of large, asymmetric ions that reduce lattice energy. The first reported RTIL, ethylammonium nitrate, melting point 12 degrees Celsius, was synthesized in 1914, but widespread interest emerged only in the late 20th century with the development of air and moisture-stable systems. RTILs have gained significant attention as green solvents due to their negligible vapor pressure and reduced volatility. However, their environmental impact is more nuanced and depends strongly on chemical composition, degradation pathways, and toxicity. Structural features and intermolecular interactions. RTILs typically consist of bulky organic cations, such as imidazolium, pyridinium, ammonium, phosphonium, or sulfonium species, paired with weakly coordinating anions including halides, tetrafluoroborate, BF4, hexafluorophosphate, PF6, and bis, trifluoromethanesilvanol, imide, TF2N. The physiochemical behavior of RTILs arises from a combination of interactions, electrostatic forces between ions, hydrogen bonding, often between cationic ring hydrogens and electronegative anions, van der Waals interactions associated with alkyl chains, dipole-dipole interactions. These interactions create highly structured, yet dynamic, liquid environments. The presence of polar ionic domains and non-polar alkyl regions often leads to nanoscale heterogeneity, which governs solvation and transport properties. A key advantage of RTILs is their tunability. By modifying cation structure, e.g., alkyl chain length, or selecting different anions, properties such as polarity, hydrophobicity, viscosity, and thermal stability can be systematically adjusted, leading to the concept of designer solvents. Physiochemical properties. Melting behavior. The low melting points of RTILs arise from reduced lattice energy due to ion asymmetry and charge delocalization. Melting behavior depends on ion symmetry and size, hydrogen bonding capability, van der Waals interactions. Many RTILs exhibit supercooling and may form glassy states rather than crystalline solids. Alkyl chain length influences melting points nonlinearly, reflecting competing packing and conformational effects. Density. RTILs typically exhibit densities between 1.0 and 1.6 grams per centimeter cube, often exceeding that of water. Density decreases systematically with increasing alkyl chain length due to enhanced free volume. Viscosity. A defining limitation of many RTILs is their high viscosity, often 100 to 1000 times greater than conventional organic solvents. Viscosity depends strongly on ion size, symmetry, and intermolecular interactions. For example, triphenylamide TF2N-based RTILs generally exhibit lower viscosities compared to PF6 analogues. Reducing viscosity remains critical for improving mass transport in industrial applications. Surface tension. Surface tensions of RTILs, approximately equals 30 to 55 millinewtons per meter, lie between those of water and hydrocarbons. Increasing alkyl chain length lowers surface tension, reflecting enhanced hydrophobic character. Thermal stability and decomposition. RTILs are often thermally stable over broad temperature ranges. However, certain anions, for instance, PF6, BF4, are susceptible to hydrolysis, generating corrosive byproducts such as HF. Stability is thus highly dependent on chemical composition and environmental conditions. Solvent properties and mixture behavior. RTILs exhibit remarkable solvation versatility, dissolving a wide range of organic, inorganic, and polymeric species. Their dual polar-nonpolar nature enables interactions with diverse solutes. In liquid-liquid equilibria, RTILs often show partial miscibility with organic solvents and water. Small amounts of impurities, particularly water, can significantly alter phase behavior and thermodynamic properties. Predictive models such as COSMO-RS have been employed to estimate mixture properties and guide solvent design. RTILs also exhibit notable gas solubility characteristics. Carbon dioxide, in particular, shows significant solubility, enabling applications in gas capture and separations. Additionally, supercritical CO2 can be used to extract products from RTIL phases, facilitating separation processes. Synthesis and purification. RTIL synthesis generally involves two steps: alkylation of a neutral precursor, for example, amine or heterocycle, to form an intermediate salt, anion exchange, metathesis, to introduce the desired anion. Control of reaction conditions is essential to avoid side reactions and ensure product purity. Techniques such as microwave irradiation, ultrasound, and continuous flow synthesis have been explored to enhance efficiency. Purification is critical, as impurities, e.g., water, halides, significantly affect physical properties. Common methods include recrystallization, vacuum drying, and treatment with sorbents such as activated charcoal or alumina. Applications. RTILs have been explored across a wide range of applications: green solvents for organic synthesis and catalysis, electrolytes in batteries, fuel cells, and supercapacitors, separation media for extraction and gas capture, lubricants and tribological fluids, advanced materials, including polymers and nanocomposites. Their tunability allows optimization for specific processes, often enabling reactions or separations that are difficult or impossible with conventional solvents. Handling, stability, and toxicity considerations. Despite their reputation as environmentally benign solvents, RTILs require careful handling. Many systems are hygroscopic, and water uptake can significantly alter properties. Additionally, hydrolysis of certain anions can produce hazardous species. Toxicity is an active area of research. Trends suggest that toxicity increases with alkyl chain length. Due to increased lipophilicity, aromatic cations tend to be more toxic than aliphatic analogues. Both cation and anion identity influence biological effects. Thus, the green nature of RTILs must be evaluated on a case-by-case basis. In conclusions, room temperature ionic liquids constitute a rapidly expanding class of functional materials with highly tunable properties and broad application potential. Their unique combination of low volatility, thermal stability, and structural versatility makes them attractive alternatives to conventional solvents. However, challenges related to viscosity, purity, stability, and toxicity remain significant barriers to widespread industrial adoption. Continued development of predictive models, standardized characterization methods, and environmentally benign formulations will be essential for advancing the practical use of RTILs.